Okay, so a couple of things I do want to go over. So the last couple problems on that Connect assignment, probably the easiest way to do them is kind of use Excel, right? So you don't have to use like necessarily the built-in functions. We haven't covered like, I'm almost positive there's a covariance and correlation function built in. If you want to use those, that's fine. But the way we talked about in class, you could have also done it that way, right? You could have like created a new column where you look at the difference between X, another column where you look at the difference between Y, multiply those two together in another column, right? Use the sum function to add those all up, use the count function to count the number of observations, right? So I would suggest in those last couple Connect homework questions, try to use these different things in Excel. If you want to use the built-in function and Google it and try to figure out, that's fine. But I would start, I kind of want you to get used to using what we've talked about at this point, using the sum functions, creating new columns, using that count function to get the number of observations, and then kind of do it almost like you're doing it by hand, just using Excel to do some of like the real mundane, like adding it, doing it for every single observation. You can like double click and have it do it all at once. Is that clear what I'm saying on this? No? If it's not, it's fine. You can tell me. Okay. I put an announcement up as well. 11 and 12, don't worry about the questions asking about MAD. I'm going to go back in after the due date, give everybody full credit for those two, part B's on those. I forgot that I knew that those were on there and I forgot to say something about it because I didn't want you guys to have to do those. If you did, you're better off for it, I guess. So it's not anything terribly different than what we've really been doing the variance. Just a different measure. I didn't want to put this up and freak people out, but I have a set of questions I'm going to put up on Canvas, and I'll probably call it like sample quiz. It looks like a quiz or something. Not for points. You don't have to turn anything in. I'm just going to upload it under files. So, and then I'll put the answer key up there as well. So every couple of weeks, I'll try to get one of these kind of like small quizzes up, which are basically just questions you can look through to get an idea about, okay, what's the exam going to end up looking like, right? Some, a combination of all these little quizzes along the way. But it just gives you something if you do want to kind of make sure you're, understanding everything correctly and can work through these problems, just an additional resource. But I don't want to freak anybody out thinking we got another homework assignment, So I know we've got kind of a lot going on early on in this course. Hopefully we'll start taking a little bit more of a breather here in the next week or two. Any other questions for me? I think there was something else I wanted to mention now. I can't remember what it was. Oh, there was a couple typos on the Excel. I guess I had 2 number 8s. So I went back and I re-uploaded it. If you have the original one, just label it 8A and 8B if that's easy for you. And then I referenced the stock data as murder rates at one point. I changed the example because I didn't like the murder rate data that I had, and I forgot to change it in one place. So if you ever see things like that, and you're like, what the hell is Landis talking about? Like, send me an email, let me know, like, I am human. And I try to keep examples fun. I try to switch them out and use new ones all the time. And so sometimes it might, using something as a template, I forget to, make a change here and there. That will, I'm human. So any other questions from me before we jump into material? Yeah.
Okay, the number 14, the one that we were talking about.
Yeah.
When you use the function in Excel, it gives you like -0.6 something.
And that's wrong.
But the answer, when you type it into Connect, is like 0.06.
Say that again.
Okay.
So the answer you get is what?
It is -0.674. No.
7604.
No. There's 0.6.
0.6. Oh,
496.
okay.
The answer in Connect goes by 0.067. -0.067.
You're off by a decimal. So you're telling me there's an error in the problem, is what you're thinking. Okay, I'll take a look at it. 14, you said?
Yes, 14.
Okay. It could be. Sometimes they have them. I've had that happen before where they program it and whoever was writing it up moved the 0 in their code. Okay, awesome. I see what you're saying. Sorry. Yeah, I'll take a look at that. If anyone else is having problems with that one, If it ends up having an error in it, like I'll probably just give everyone credit for it. But now that we know there might be, it's still good to like work through it and try to kind of, I guess, come up with the right answer that will be off by 1 decimal, right? So, okay, thanks for clarifying that for me. That will actually help when I go in to look at it and figure out what's going on. Okay. Was that your? All right, so week 3 lectures, right? We're going to jump off of like descriptive statistics. We're going to jump into the next thing, which is probability. So I'll put up another one of those Learn Smarts. If you do want to kind of go through that, it's not for points. It's just some additional practice if you're wanting to do that. But it'll be over chapter 4, I believe, in the book, which is all about probability. Okay. So, when it comes to probability, I think we already have a somewhat of an idea of this. Like, we talk about these things. Like, what are the chances that sales will decrease if we increase prices? What are the odds that a new investment becomes profitable? What's the likelihood of something happening? Like, all these terms are really getting at the same thing. What is the probability that something will occur, right? Or that something happens? So all these things are referencing, like, we don't like have it happen, right? What are the odds that in the future becomes profitable? What are the chances sales decrease if we change price today? What's the likelihood that if we change the selling method, right? It's all future events, right? And so it's an uncertain outcome, right? We don't know what the outcome is going to be. We know there's several different options, right? And some of these, there's only like 2, but right, if I'm talking about, will sales decrease? Well, sales could stay the same, it could increase, it could decrease. All 3 of them might have different probabilities of occurring, right? So I know that hopefully, if I've taken 201, I know that, if the price is increasing, you would think that sales would decrease would be the most likely outcome, have the highest probability of occurring. But we come up with some goofy scenarios that like are complicated past 201 when it doesn't happen. So what we're going to call these uncertain outcomes, these things that we're interested in, they're just going to call them experiments. Okay? An experiment is something that we're going to run. We don't know what the outcome is. And don't think about these like physics, right? We're not playing around with Bunsen burners and whatever other stuff, but like we're thinking about anything could be an experiment, right? What is the probability? What's the weather going to be like today? Right? That's the experiment. There's different probabilities for different outcomes of that, right? Probability that it's sunny, rainy, snowy, so on and so forth. So what we're going to do is we're going to run these experiments the exact same way, right? So if we ran them over and over again, we could get an idea that like we can see different outcomes. So if I draw a card from a deck, 52 card deck, that's an experiment. Right? I don't know what card I'm going to get. Right? I know that there's let's say I ignore the suit. Right? There's 13 different cards, right? 2 through king, or start them. Ace through king, 2 through ace, however you want to put the ace. And I know that with a card deck, they're all equally likely outcomes, right? Because there's 4 of every single card. When I'm running this experiment, I start to realize if I've never seen a card deck before, if I pull the first card out, okay, I guess I can get a queen, right? But I don't know what cards look like. Oh, there's numbers too. I can get a 4, right? So I start running this experiment over and over again. If I did it enough times, I would realize all the different possible outcomes that would exist for drawing a card from a deck. So these experimental outcomes are going to be any outcome that I could see when I run this experiment. And ahead of time, we might not know what all of them are, right? If I don't know the cards that are in a card deck, like any of you guys know what Rook is? Nobody knows the card game Rook? Oh, it's a great game. It has goofy cards. It has a Rook card, right? If I don't know the game of Rook, right, I don't know how high the numbers in that deck go. I don't know if there's kings or jacks or whatever. And so the only way I can realize all the experimental outcomes is probably running this experiment a high number of times. The sample space would be all the outcomes I see as I run this experiment, right? So it may be that, if I've only drawn 10 cards out of a deck, I haven't seen every different possible card that I could draw. So my sample space might not, it's going to tell me what possible outcomes are, but it might not have every possible outcome. Depends on how many times I've run the experiment. So my sample space is kind of like, could be smaller than my number of experimental outcomes. And then we might just be interested in a specific event. So once I draw, I draw a card from the deck 10 times, I might say, okay, well, how many times did I draw a king? That's the event I'm specifically interested in. And that's going to be some subset of my sample space, right? I'm going to have all these different outcomes I saw, and I'm interested in one or two of them. Okay? So kind of visually, right, we've got all of these experimental outcomes. As I run the experiment, I see a bunch of different outcomes in my sample. And then within that sample, I might be interested in only specific outcomes. We'll call those events. Okay? You kind of think about sample space, it's kind of like a data set, right? If I drew the card and then like draw one, wrote down what I saw, draw two, wrote down the card I got. I then have a data set, maybe a qualitative variable, and because it's we got jacks and kings, but I'd still be able to create a data set like this. Okay? So we think of other examples, right? If I flip a coin, this is like the easiest one. What are the only possible outcomes I could see? These ones are easy, right? I know ahead of time I can see heads or tails. If I roll a die, I'm playing like Dungeons and Dragons, like a normal die, right? I see 1 through 6, right? Choose a card from the deck, ace to king, playing a football game, we'll say postseason, win or loss, like a soccer game, regular season, win, loss, tie, right? They're just anything can be an experiment. Now we're going to have different probabilities of each one of these occurring. Now in some of these examples, these are pretty easy, right? I know the probability that I see any one of these numbers, like unless I've like weighted this die, they're all going to be the same. When it comes to things like winning a game, well, if I've got different quality teams, I know that the probability that, for instance, who will I pick on? Oh, the probability that I have the unfortunate of being a Lions fan. So the probability that the Lions beat the Chiefs is very small, right? They could win, but the probability they win is much, much lower, right? So there are going to be a lot of experiments where probabilities aren't equal, right? But some of the easy toy examples, they'll be equal, right? So this is kind of mention this, right? But we're thinking about we have these different outcomes, right? And the different outcomes have different probabilities. Well, it could be that we don't just want to know about one outcome, we've got several outcomes, right? So for the card, it could be the event I'm interested in. Well, what's the probability if I draw a card from the deck that I get, a jack, queen, or king, right? Multiple outcomes within one event. Right? You can start to think about how we calculate the probabilities of an event like that. So this is all just kind of definitional stuff. But if I'm thinking about, I am interested in an event, the probability of the event, what we'll start to notate that is the probability of whatever the event is, right? P, and then in the parentheses, the outcomes or kind of outcome that we're interested in. So this probability, lowest chance that something occurs is 0, right? 0% chance something occurs, kind of a negative chance that something occurs. And if something is a sure thing, there's a 100% out, 100% likelihood it occurs, or as in terms of a probability of 1. So probabilities are going to be just like those relative frequencies that we were looking at, right? The smallest they could ever be is 0. The highest the probability of an event can ever be is 1. Right? The probability I draw, from a 6-sided die, the probability I roll a 10 is 0. Right? But if I'm thinking about, what's the probability that I don't know, what's something that is guaranteed? What's the probability that if I draw a card from a deck, I see something 2 through ace, right? Or ace through king? Well, that's every possible outcome. I'm going to see one of them. The probability would be 1. Right? We don't usually, deal with examples like that because they're not very interesting. But our probabilities live somewhere in that range, 0 to 1. If we look at every possible outcome, right, the probabilities of every possible outcome have to add up to 1, right? So you kind of think about if I'm flipping a coin, the probability I see heads is 1/2, the probability I see tails is 1/2, right? Add up the probabilities of all outcomes, there's only 2 here, I get 1. If I think about the dice example, right? 1/6 over 1/6, right? Those would add up to 1. If I'm thinking about my example of the Lions and the Chiefs, right? The probability they win might be, 0.02. Well, so we'll ignore ties for the sake of this example, but the probability they win is 0.02, which means the probability they lose, it's the only other outcome, would be 0.98. Add those up, those have to add up to 1. I could put in the probability of a tie here if I really wanted to. I just was feeling lazy with that example. And that kind of makes sense, right? If I look at every possible outcome, one of them has to occur, right? So if I add up all those probabilities, it should add up to 1. And this is to link this up with some things we talked about. Remember when we were doing the relative frequencies? So relative frequencies, I'm telling you, you can kind of think about as probabilities. We said the relative frequencies should add up to 1. Same idea here, right? And it's because we were looking at the relative frequencies for every possible outcome for a variable. Every possible outcome here, it's probably should add up to 1. So how are we going to assign probabilities? Okay, I want to get focused more on other things. So I'm going through this stuff a little bit quicker, but we'll have some examples that we work through and start dealing with probabilities. So we can classically assign them. This is really easy. These are our toy examples where I know that seeing a heads and tails is equally likely. I know that any number of die is equally likely. I can just basically assign every outcome the same probability. But what probability is that? Well, if we look here, if I had a coin flip or I was rolling a dice, 1/2 and 1/2, 1 6, 1 6, 1 6. How was I kind of getting those probabilities? I was taking 1 and dividing it by the number of possible outcomes I could see. Right? If there's 6 outcomes, they're all equally as likely. The likelihood I see any one of them is 1/6. If I had 100 different outcomes, right? The probability I see any one of them, if they're all equally as likely, is 1 out of 100. 1 out of total number of observations, or total number of experimental outcomes. Sorry. So that one's not terribly interesting. The empirical method. This is going to be the one that is probably, kind of a subjective statement, but you would want to use 99% of the time, right? So this is going to be where you've seen this experiment run several times in the past. You're going to use some historical data to then try to come up with what the probabilities will be in the future. That makes the most sense, right? So we're going to use data to then kind of assign probabilities. And I'll go over this on the other slide, a little bit more detail in a second. And then the subjective method. Right? So this is going to be where we just assign probabilities based off of our knowledge. So that might seem kind of hokey, but we'll talk about some situations where the subjective method makes sense. So classical, kind of already walked through, so very easy. Just the probability of every outcome is going to be 1 over the number of possible outcomes. Okay, we got our coin flip, rolling a die. That one, kind of already talked about that. Let's say I flip a coin twice. Well, now the different combinations I can see, I can get heads first, then another heads in the second, heads, tails, tails, heads, tails, tails. So there's 4 different combinations, if I care about ordering, that I could see that, the 4 different results I could see when I flip a coin twice. So the probability of each one of these outcomes would be, 1/4, right? 4 different outcomes. I'm using that classical method, just 1 over the number of outcomes. What about empirical, right? So this is the idea, this is a dumb example, but let's say I'm interested, if I chose someone at random, what's the probability their favorite cuisine is? I can't choose Mexican food here, but whatever you're interested in, right? And maybe it's, you want a different type, but I might look at a data set where people were surveyed, and I see in that data, 15 out of the 60 individuals kind of chose Mexican cuisine as their favorite. So I know if I choose one person at random, one student at random, well, based off historical data, the probability would be 15 over 60, or 25%, or a probability of 0.25. So I'm just using some survey data, right? What I know about students, let's say Ball State, maybe these were Ball State students. So now if I ask a person at random, and it's an uncertain outcome, I don't know what their favorite cuisine is going to be, but based off of 60 other students, I know the probability they respond with this specific response would be, whatever the data tells me. This is more practical, where let me think about a good example. So every day, right, we could see different types of weather. Right? We know there's different probabilities of occurring based off of historical records about the weather on that day, right? First week in September, looking at historical data, the probability that it's 40 is very, very low, right? So, we don't know what the weather's gonna look like tomorrow or next week. And I got really into this for a while, but has anybody ever heard of chaos theory in mathematics? So this is the idea that in a very small range, I know where a function might be going, right? But over the long range, like it's doing all this kind of crazy stuff, and I'm not able to predict it, right? So the weather is like operates under chaos theory, and that like within the next week, I can be pretty accurate at predicting the weather. But like 2 years out, not as easy to predict like what the weather patterns will be. However, if I use historical data, right, I can actually come up with pretty good predictions. Now they're going to be off year to year because maybe the first week in September, one year had what do they call like cold front moving in, while another year there wasn't. But I'm going to be making kind of small errors if I use that historical data. So we look at like what has the weather been like on this day the last 50 years, take the probability of it being 60, the probability of it being 70, so on and so forth. And that's kind of the idea of empirical probability, or assigning things over. Now, the one that seems like the biggest crackpot is this subjective one, right? I just start assigning probabilities because I know everything or something. Well, okay. I mean, it's not that we're just like throwing numbers out without any justification, right? It's going to be something like if I was looking for a CEO of a company, right? And I've got 4 candidates. You might say, well, they're all equally as likely they got the interview. Well, who knows? Maybe some of them are just there, like they really only, they like these 2 guys a lot, but the other individuals, they just kind of had to fill the quota for how many people they interviewed, right? So you might know ahead of time. I'll give you an even more extreme example. Let's say this Andy guy, right? He works at the company, right? And he was kind of, I don't know, working right underneath the CEO. They fired their old CEO and they really want to hire him. They want to hire him, but HR says you have to interview at least 4 candidates. Well, in that situation, the probability that Andy gets the job is like 0.9999, right? They want to hire him. These 3 people are just to fill their quota to interview, a certain number of individuals. They can't just give the job to an internal applicant, right? Or it might be something like, well, maybe, Chung has run a company before, Andy's the janitor. Like if you have differences in the resumes, some of these individuals are going to be way more likely to get that CEO job than others. So when it comes to a situation like that, we don't have historical data. We can't run the interview process to be the CEO. We've never done that in the past, right? It's for completely new candidates, right? Maybe there's some CEO position that the same 4 people have applied to, but I highly doubt it, right? Or more than once. So, maybe based off their resume, what we know about the individuals, we know that certain candidates would be more likely to get the job than others. The only thing we have to make sure when we assign the probabilities this way, we need to make sure they always add up to 1. Any questions on this? It's kind of like definitional, kind of getting us set up for probabilities. It's a little bit more difficult problem. So subjective probability. So welcome to probability statistics, the class where everything is made up and the numbers don't matter. So you guys know this show, right? Kind of had like a reboot. So okay, great show. What's the guy? I looked these clips up. It's like last year. The real tall guy. Is it Ryan? Yeah, he's my favorite. He's my favorite. Anyways, I'm going off on the side. So we'll start to think about how we can do this more generally, how we're going to write out probabilities. So one thing that we'll use is kind of this idea of complements. So a complement, we're going to be thinking about this event A as whatever we're interested in, right? This could be, drawing a king or on a deck or getting heads on a coin flip. So let's start to think more generally about this. Let's say I have event A, and this isn't maybe like the perfect notation, but so I'm going to do, let's think about rolling a die. That one's probably a little bit easier. So we'll do 2, 3, or 4. That's like our event that we're interested in. Event A is if I see a 2 or 3 or a 4. A complement is everything that's not in event A. So if I roll a 6-sided die, what would a complement be here? yeah, just everything not in A, which is 1, 5, or I should say, all the outcomes that are not in A. So that's how we kind of notate a complement, was like using the superscript. The union of two events, right? We're going to write A, and this is kind of a set sign, right? So A union B. This one's a little bit easier to remember. It looks like a U, right? A union B. So the union of two things is it in event A or is it in event B? It can be in either one. So let's say I had event B here. And I do 3, 4, and 5. So A union B would be anything that's in A or in B. So another way to think about this is, so this is my union, or the way that we kind of read it, or we say is or, A or B, or A union B. So here that would be what? 2, 3, 4. If it's in both of them, we don't repeat it again, right? It's the same number. So 2, 3, 4, or 5. So A union B would be 2, 3, 4, 5. Those are all outcomes that are either in A or they're in B. They can be in both, right? There's some that are in both, but it just needs to be in A or in B. Those are all the possible outcomes we could see. What about next one, which is the intersection? This is like where the two events overlap, right? So it's going to be outcomes that are in both of these. So when we write A intersection B, so intersection, usually we would read this as A and B, right? Is it both in event A and in event B? And I don't know, some people say you can remember it as like you draw a line through it, it looks like an A, but I don't know. I mean, union's pretty easy to remember that it looks like a U, and then the other one's the intersection, right? So I don't know. If that helps you, that helps. But so A intersection B would be anything that's in both of these events. So what would my intersection be here? Yeah, right. The only outcomes that are in both are 3 and 4. Okay. Any questions on any of that? So we're just kind of using that notation now for the complement, union, intersection. We'll start playing around with this a little bit. The last one we have, it's a little bit more complicated, is given. So what's the probability we see A given that we know B has occurred? So it's kind of a weird one to think about since we don't have probabilities yet. But when we write this vertical line, we're saying, look, I'm telling you event B has occurred. Like whatever's on the right-hand side of that line, I'm telling you, I already know this has occurred. So if event B has already occurred, I know that when I rolled that die, the number that came up, it's a 3, a 4, or a 5. Like I'm telling you that it's event B has occurred. It's one of those numbers. So now that I know event B has occurred, what are the outcomes in A that I could see? So if I'm telling you event B has occurred, what are the only possible outcomes now that I could see from event A? Not quite, right? 2 is the only one that's not an event, right? So it's kind of like if I'm thinking about where they overlap, that would kind of be like the conditional probability here, right? Given that I know B has occurred, the only outcomes I could see from A now are 3 and 4. Because I know either a 3, a 4, or a 5 was rolled. I don't know what it is yet. I just know that I know event B happened, right? Because it's on the right-hand side of that line. I'm telling you event B has occurred. Well, I don't know which of the outcomes in event B occurred, but I know one of them did. So I automatically know that I can't see the outcome of 2, right? The only outcomes in A that I still could see would be 3 and 4. It's a little bit hard of an abstract idea at this point. Once we actually have start talking about probabilities, the conditional kind of thing makes sense. But like we'll go over the first 3 first, and then we'll kind of revisit this conditional probability later on. Yeah.
So were you rolling more than once?
No. So like let's say I roll a die, right? And I don't know what the number is. I can see it, you can't. Right? I go, okay, the event you're interested in, like maybe you put a bunch of money, but it came up 3, 4, 5. Doesn't matter which of those numbers it is. If it's one of those numbers, you win a bunch of money. So I go, or sorry, maybe you put money on that event A has occurred, right? So if you put money down, you said, okay, if it comes up 2, 3, or 4, I win. So I look at this and I go, well, I'm not going to tell you what the number that I can see is. But what I will tell you is event B has occurred. Well, event B isn't seeing all of these at the same time. It's that I saw one of these. You still don't know which number it is. So now you're thinking about your bet and you go, hey, maybe I feel a little bit better. I mean, I know that it can't be 2, so I know one of the numbers in what I bet on, I'm kind of screwed. But at least like there's a lot of overlap and it's likely I saw the other 2. So that's kind of the idea of like, we're interested in multiple outcomes within that event. In practice, usually we're more concerned with like the probability of one specific outcome, but we can group, we might be interested in like, if I put the, I might think about, I'm not just interested in one value, I'm interested in like a range. Is it in this range of outcomes? But like I said, these conditional probabilities or conditional makes a little more sense once we get to conditional probabilities. So we'll hammer this a lot more, probably Friday, because I think we'll, are we on time today? Yeah, we'll probably won't get that till Friday. So we'll focus on those first 3 for the rest of today. We'll start using Venn diagrams a lot. So this huge square represents every single possible outcome. Like I'm trying to use it as a visual for every possible outcome. So what would the area of that square be if we're thinking about probabilities? The square represents every possible outcome. Sum of all the probabilities for every possible outcome should always add up to 1. So that square, the rectangle, I guess it's not a square, not a rectangle. The area we'll think of as 1, right? So this visual is trying to represent probabilities. Every possible outcome is in this rectangle, so the area of that rectangle. We then have different events, so A and B. So A might include several outcomes, B might include several outcomes, right? We're going to draw that visually with, okay, this circle of A, this includes all outcomes that are in event A, and the circle B, all outcomes that are in our event B. Any questions over kind of just that idea of using these circles? So where these 2 things overlap, right? These are going to be outcomes that are in A, but they are also in event B. So if we were trying to make a nice visual of this, like that intersection section where they overlap would be like 3 and 4 would be outcomes in this space. The union of 2 events is, well, it could be an outcome that's in A, but not in B. It could be an outcome that's over here in B, but not in circle A, or it could be an outcome that's in both. Right? So the union of 2 events is kind of like, I could be in either circle. I don't matter. It's in this one or it's in this one. So what's something that you maybe notice about the union and the intersection? What's something that will always be true about the union and the intersection? So I kind of just broke down that union into 3 parts. What was one of those parts? I said it could be an outcome that's in A, but not in B. An outcome that's in B, but not in A, or it could be in both. So the union will always include the intersection, right? The union is always going to include the intersection. Any questions on this? So we will use these visuals to get the concept down a lot of the time, but the actual numbers, we're going to be using these contingency tables. Right? So I'll keep it pretty basic to start out with, where we only have 2 events, A and B. And we can think about their complements as well, right? If I'm interested in event A, well, there's always going to be a complement. Okay? So let's say event A here. The way that I determine what the probability of A occurring is I go over to these totals. So these totals represent the probability of the row and column height. The probability that B occurs, 0.5, probability B complement occurs, 0.5, probability A occurs is 0.6, and the probability that A complement occurs is 0.4. So those total columns represent the probabilities of the events themselves, right, on the row and the column headings. So also can kind of think about, actually, I'll come back to this in a second. The top 4 left cells all represent intersections. So this is the probability of A and B occurring. This would be the probability that A complement and B complement occurs, or that A or B don't occur. So those top 4 left cells represent the intersections of the row and column headings, and the totals represent just the probabilities of the events themselves. So we'll go back here. I was writing this as the probability of A. I told you when we read this table it goes 0.6. But even if I didn't see that 0.6, the way I can get these totals, I could have just shown you these bottom 4 left cells. And if you add across, notice you get the totals there. And if you add down, you get the totals here. So why does that work? So if we think about what we're doing here, got event A and event B. Okay? If I'm interested in the probability of A, I can break the space of A down into like 2 components. So what's this component? That would be the probability that I'm in A and I'm not in B. Right? Every outcome here is in A, and it's crescent moon, but it's not in B. What is not B? B complement. Kind of give you another visual on this as well. Why that's the intersection of A and B complement. What would B complement be? So if I was drawing this out, and I just had B, B complement is everything else in the space outside of this circle, right? So here, B complement is this entire space. Notice where A and B complement intersect is just this area right here, so crescent. So the probability of A and B complement represents this part of event A. If I then wanted the other part of A, what does that represent? Showed you on the earlier diagram, right? This is just where A and B overlap. So I would call that the what of A and B? Yeah, the intersection of A and B. So if I add this blue area up to kind of this black area, and I know what they both represent now, well, notice what's this? The probability of A and B. This is the probability of A and B complement. The first thing, right? So if you think about anywhere where A and B overlap, and then anywhere where A and B complement overlap, well, that's every possible outcome we could ever see in event A. So if I add those 2 things together, that would just give me the probability of A occurring. I think about it this way. Let's say I had example probability. Okay. Let's say I'm interested in the probability that I walk outside and I slip and fall. That's what I'm interested in. And let's say event B is that it is raining. Right? So event B is that it's raining. So I would have the probability that I slip and fall when it's raining, and then plus the probability that I slip and fall B complement. It's not raining. Well, there's only 2 out, right? Like I'm thinking, or there's precipitation or not, right? Well, that's every possible other thing that could occur. So the probability I slip and fall will just be the probability I slip and fall when it's raining, plus the probability I slip and fall when it's not raining. That's what we're saying here. Probability that A occurs and B complement occurs, plus the probability A occurs and B occurs. That would fit any time that event A would occur. So that's how we can add across the rows and down the columns and it works. Left everything over here. Any questions on that? So we've got our totals. Also kind of notice the totals add up to 1, right? If I add down or across, they add up to 1. So why would that work? So what am I really doing here? I'm taking the probability of A plus the probability of A complement, and I'm saying those add to 1. It's kind of similar to the idea of what I was just talking about. A little bit different. So let's think about, I'm just interested in the probability I slip and fall. I don't care about the weather. If I walk outside, the probability I slip and fall is maybe 0.1. What's the probability I don't slip and fall? It's the only other outcome, so I have to add up to 1, so 0.9, right? That's what's happening here. The event and its complement, right? Those probabilities will always add up to 1. So the probability of A plus the probability of A complement will always add up to 1. Okay, which gives us, we might jump ahead here. Skip this. The complement rule, right? Visually, if I take the probability of A and add to that the probability of A complement, that fills out the entire experimental outcome space, which we said that area represented 1. Right? It kind of comes from this guy. Notice if I rearrange this, I can get that the probability of A is equal to 1 minus its complement, or vice versa. If I want the probability of the complement, it's 1 minus the probability of A. But that complement rule is really coming from this kind of intuitive idea, right? Probably that A occurs plus the probability that A doesn't occur. That's every possible outcome, right? Questions on that? Yeah.
So if there was a B, A complement would not include B, would it?
It depends. Depends on the example, right? I guess I could I have a weird one where here's event A and event B is like a subset. If they, more often than not though, right, we are going to have some overlap. And so there, right, B would be in parts of B would be in A and parts of B would be in B or A complement.
Okay. So A complement wouldn't include the circle that's sort of overlapping.
It wouldn't include that. Right? So have it over here, right? So right, we had this. Here was everything that was in A. It included part of event B. A complement would be like anything outside the circle, which notice anything outside that circle of A includes part of B as well.
That's what I was asking.
Yeah, yep. Yeah, but it could be that it includes stuff that's in B, but also stuff that's not in event B as well. Okay. All right, we'll go back. So this one hopefully won't be too bad. Kind of get people points for showing up today. Kind of get an idea about hopefully that you're all kind of understanding where we're at. I can look at this after class. So let's say I had R1 and C1. And here I'm just calling C2 and R2. Those are essentially the complements. Right? Just a little bit of a different notation. So if I wanted the intersection or the probability of the intersection of R1 and C1, which of the following would that be? So I'll give you, we'll go to 45 seconds or a minute. Shouldn't take too long. Right? We talked about what the totals represent. We talked about what those top 4 left cells represent, which they represent those intersections. So I want the intersection of R1 and C1, that probability, which of these answers would it be? Give you guys a second to make sure everyone gets an answer in here. Should have 11 people. 1, 2, 3. Oh no, I think. I'm crazy. 5, 5. Okay. All right, 13. We'll close it out. So, what should the answer be here? So those top 4 left cells represent intersections. So the intersection of R1 and C1 is just 0.3. So we're going to start using these contingency tables a lot. So we need to be comfortable with knowing those top 4 left cells represent the intersections of the row and column headings. The totals represent the probabilities of just the row or column heading. We'll end with some stuff so we don't have to go over it. Starting on Friday, we can kind of dive in a little bit more into this. I think we'll do some Excel work on Friday as well. So I think I actually put the files up there already on Canvas. You might have seen them. We'll work with those, but to kind of end before we leave, when we're writing these out, it doesn't matter the order in which we write. Okay, so our first probability law, well, I cheated. I showed you the confident one. So I guess the second probability law we're looking at. It doesn't matter if I say, okay, what events are in A or are they in B? Well, that's the same area as if I say, what's the probability that the outcome is in B or in A? It doesn't matter which order I say it in, it's still talking about the same space. And so visually, we want to like shade this in, right? A union B is just, is it in A or is it in B? So, and I always like this, when you say it's fine, when it's actually fine, right? The intersection is basically non-existent, right? But we can think about, when we're talking about the intersection, it doesn't matter which way we say it either. Well, what's the probability that this occurs and this occurs? Or sorry, what's the probability it's raining and I slip and fall? What's the probability I slip and fall and it's raining? It's talking about the same thing, right? So order doesn't matter when we're talking about the union or the intersection. Once we get to conditional probabilities, it really matters. But with the intersection and the union, it doesn't matter at all. That'll help us out with some of the other probability laws that we'll go over on Friday. We talked about the complement rule. We'll use kind of this idea that order doesn't matter. We'll talk about kind of the spaces, and we'll start out on Friday with the addition rule, walk through some more probability examples, introduce conditional probability, and then jump into Excel. Any other questions? And then the stuff that we're going to be doing in Excel is for like not the current Excel assignment. It's just additional Excel stuff. Something that might help you on the homework assignment as well. I mentioned it, and I'll just show you very quickly. Maybe. So let's say I've got any data set. Oh, come on. So notice here, when you downloaded the data, and this is a different data set that you guys have to Excel, but notice how there's like little arrows up here on the variables. So on the home price one, I already had it set up to be filtered. I thought I had the other one set to be filtered as well. If you want to create filters on your data, you just select, I'm using that Control Shift or Command Shift to select every variable, hit the down arrow. So I've got my whole data set selected. Go to the data tab. Notice filter was selected. So I hit filter. And what that's going to do is put those arrows up there for you. Now what you can do is sort the data, and it moves the entire rows, right? So they're all moving. So the observations are kind of not getting jumbled up, right? There's easier ways to answer that one question about the presidential election data, maybe using some like count ifs functions or something. But you could use the filter to kind of do it by using, kind of eyeball it. But I forgot that I hadn't mentioned that to you. I don't want anyone to get tripped up that was like a hint that you could also do that. Okay. All right. I will see you guys on Friday. If you have any questions for me on the way out, feel free to come up here. Otherwise, I'll be in my office hours tomorrow, 11 to 1. If it doesn't work, shoot me an email. We can set up another time.